SIN, multifunctional Luneburg lens-enabled radar for enhanced space domain awareness.
Thank you. All right, so this works, right? Yeah. All right, good morning. First of all, this is my first time to attending the symposium. Eye-opener. Thank you very much for the organizer and everybody. So the topic is a multifunctional Luneburg lens-enabled radar. So it's a radar at millimeter wave frequency for enhanced space domain awareness. I'm a professor at the Electrical and Computer Engineering Department and also Physics Department. So the objective of this project is threefold. See, maybe I should stand it, but I can't see it myself. First is a self-contained. Oh, thank you. It's over there too. This is great. First of all, we want to build a self-contained in-orbit monostatic radar that will trying to be able to detect a 10 centimeter small object and within a 10-kilometer range. So monostatic radar, for those of you not familiar with radar, means your transmitter and receiver at the same place. So you have a radar unit, sends out the signal and measures the scattered back signal, detect the objects you want to detect. The second one is for the same radar hardware, we want to be able to reconfigure the waveform and the software so that we can use it as a closer by imager, which means you will provide very fine details of things so that this may be utilized for rendezvous or proximity operations. The third one is we also would like to be able to reconfigure the same radar hardware utilizing the large power transmitter on Earth. For example, the MIT Lincoln Labs Magellan radar, which has megawatts power, that we would use that as a transmitter, but only use the onboard radar as the receiver. This will further increase the detection range, or we'll be able to, for the same range, we'll be able to detect a much smaller object. So the radar architecture is showing on the figure here. You can see that in this case, we have multiple transmitters. So it's something called a MAMO, multiple input, multiple output radar architecture. And the transmitter will sort of work like a flashlight, and it will shine the entire field of view. One of the great advantages of this is we're using a unique Luneburg lens antenna, which I'll explain a little bit if you're not familiar with it. And because of the unique antenna, this radar will have very large field of view, or even unlimited field of view with a single unit, single aperture. And it can be very broadband. We've demonstrated antennas, Luneburg lens antennas from L-band to W-band. So 2 decades of frequency is possible. And you can have very high angle resolution. Therefore, you can use it as an imager, not just the typical radar. And this type of a radar has interference mitigation capabilities. And this is all enabled by a unique 3D printed millimeter wave Luneburg lens and radar sensing algorithms we developed. And UE has, we have several patterns and trade secrets. So the disruptive technology shown here, that's what do you see there? The small spherical antenna aperture is called a Luneburg lens, and it's very broadband. As I mentioned, you can have high gain beams in any direction in the 3D space, and you can have multiple beams together. For some of the 5G wireless communication, we've demonstrated 64 beams, and you can even have hundreds of beams, and there's no scan angle limitation. So just a little bit about the Luneburg lens antenna in case you're not familiar with it. It belongs to an optical device called gradient index devices. If you can build an antenna or lens that you can control the material property, for example, the index of refraction or dielectric constant as a function of location, you can have very nice flexible designs. You can have a flat lens, very thin lens that can focus. You can have the classic Luneburg lens or Eaton lens, etc. Even the human eyes has gradient index lens, which the index of refraction varies about 4%. That actually makes our eyes much better than most of the camera lenses. However, so the people know about this a long time ago. However, it's traditionally extremely difficult to manufacture them. So for example, I'll show a Luneburg lens here. A typical Luneburg lens is on the top right, and you can see that it has a spherical shape. If you can have the dielectric constant of that lens is equal to 2 right at the center, and if it gradually reduces to 1 at the edge of the lens, just follow that equation, you have very nice antenna property. For example, you put a point source on any point on that surface, you have a collimated high gain beam going out. This is true for every single point on that lens. You can imagine you can put light bulbs on the lens and you can have a laser focused beam going into all directions. Same is true for receiving, right? It's all reciprocal. People knows about it. Professor Luneburg himself invented this concept in the 1940s. It didn't occur until the 80s that some type of a physical prototype came out because it's just so hard to implement it. What people were doing is it's like you're building an onion. You start at a dielectric constant equal to a little core. You take the same material, dilute it, you add a layer to it. You keep diluting it, add another layer to it. You can imagine the layer thickness needs to be sub-wavelengths, needs to be very thin. And the material property needs to be very precise. So it's extremely difficult to make it. There are companies making it, but it would only work to about 6 gigahertz, maybe 10 gigahertz. And for those fist size lens, it will cost you $1,000 or a few $1,000s. If you want a larger lens and higher performance, I know AT&T paid $250,000 for a 1 meter diameter lens. It's all because it's so difficult to make. Until 3D printing technology get more matured. So in 2007, that's the first time I bumped into a 3D printer, and we realized how fine the structure you can have. So we started to design a Luneburg lens in 2 years. In 2009, we built the first one. And you can see an example CAD at the bottom right. We digitize the lens into thousands of little chambers. Each chamber is designed by mixing 3D printable polymers and air. So you can imagine if I have a dielectric constant equal to 3 for the 3D printable material, I put in some voids, and I use just simple effective medium theory. I can get anything from dielectric constant equal to 1 to 3. That's how we implement the lens. And this type of lens is highly desirable in wireless communication and sensing because you get away from using planar phased array, which is the typical approach, which are expensive, has a number of disadvantages, which I'll talk more. We have demonstrated capability using 3D printing to mass producing industrial scale lenses at millimeter wave frequency or even up at terahertz frequency. In fact, we have a nanoscribe 3D printer that prints at about 100 nanometer scale. We demonstrated IR Luneburg lenses. But that's not the topic today. So from the system point of view or application point of view, think about a radar. Typical radar uses this planar phased array. You have large number of elements, you control the phase and amplitude, you can scan the beam, right? There is a limitation. You can only scan to about plus or minus 45 degrees or maybe 60 degrees. And even with that, that's a theoretical limit. Even with that, when you scan away from the bore side or right in front of you, your performance degrades. Your beam becomes widened. So basically that means you lose signal strength, you lose the beam width, the range and angle resolution take a bigger hit. And typically when you combine this large number of signals together, you lose signal to noise ratio too. And this type of a planar array is also typically very narrow band. That means for a radar, you have low range resolution. On the other hand, With a Luneburg lens, is you have very large bandwidth, you have very high range resolution, and your performance would be uniform in all directions, even for the entire 4-pi solid angle. And no scan angle limitation means you have much better resolution, much better range at large angles. And there's no grating lobes or mutual coupling issues, and calibration is much easier. Those are some of the complicated challenges in designing a typical planar phased array. So showing here is the Luneburg lens radar architecture we invented, and UASI has the pattern. This is the 180-degree field of view design. So you can see we have this Luneburg lens at the center. Behind it, we put a little receiver around it. And then I use my transmitter as a flashlight. I just send a signal to the field, to the entire field of view. In this case, 180 degree. By the way, no other antenna can do this. And then the signal bounced back from your target. In this case, this is for ground applications. So we demonstrated this a lot in ground applications at the TRL7 level. You see the signal going from the car gets focused by the lens to a single channel behind the lens. Same thing for the person. So before I do any signal processing, I know that car must be coming from 30 degree from east, and etc. And then if you do some little more signal processing, you can get much better resolution. So you have reduced processing requirement. And that's a big deal for some of the airborne, because that's basically your power and cost. And the calibration is much easier because your beam is formed. How much time do I have? Okay. And so you can see that because the beam is formed by my physical aperture, I'm not using fancy electronics, phase shifters, and etc. So it's not temperature dependent. If you're familiar with planar phased array, for a large array, you spend 50% of the cost on testing and calibration. And that's a big deal. So this type of radar doesn't have that issue. And because of the focusing capability, you have enhanced signal to noise ratio. And it's actually proportional. If you go through the math, proportional to square root of n. N is the number of elements you have. So if for a ground-based application, for vehicle, for autonomous driving, this type of radar typically have 16 elements. So you have a factor of 4 or 6 dB enhancement in signal to noise ratio. That means longer range. That means you can do fancy super resolution angle finding, etc. Another big advantage is it has intrinsic interference mitigation capability. Imagine I have a jammer coming in. What's going to happen is only going to impact one single channel. All my other detections will be completely fine. And with that, it's much easier to detect your interference, and we demonstrated various mitigation capabilities. From a system point of view, because each radar now has much bigger field of view, you only need less number of units. So showing here, I will, just because of time, I'll skip the details. This is a calculated radar coverage map using exactly the same electronics, but different antenna. The purple region in the middle is a planar array antenna. You can see it can only cover 120 degree field of view, and the range is much less. The angle resolution is much worse. But with the Luneburg lens radar, this is a 180 degree design. We could actually have 360 degree design if needed. So this has been demonstrated for ground vehicles. And you can see the radar prototype used here. It's about 10 centimeter by 10 centimeters. It's very small, about your cell phone size. And the top figure here shows the ground truth. That's a camera image. You have a tree, you have a rock. You can see the radar image. You clearly see the tree and the rock. This is a few objects in the desert, and you can see this is the XZ cut. You can clearly detect the height and the person and the wooden pole. This is a detection of a small UAS. This is a Phantom 4. We tested. We could only fly to 400 feet without permission. So you can see we detected taking off from the ground and goes up and hovers around and come back down. This is a video we took from, this is driving on Mountain Lemon. So this was an Army-funded project for off-road detection. The color map are the height of the object. You can see the trees are tall and the snow and things on the ground are lower, but you can clearly see the drive paths. So this is, this was for ground vehicle. So now going back to space, which we don't have a lot of experience. That's why we're here, looking for collaborators. We did work with the Space Force on a couple of smaller projects related on this. So we proposed a novel radar architecture that's already demonstrated for ground applications. We've already studied the 3D printable materials that can be space qualified. We did an initial Luneburg lens, fabricated and characterized. They work pretty well. We're continuing to optimize the design and fabrication with those new materials. We did do a complete radar link budget and resolution analysis. We studied X band, Ka band, and W band. Turns out Ka band, about 35 gigahertz, is the sweet spot if we consider the size of the antenna aperture, the cost that exists, and also the commercially available chipsets, and also what's existing for the big power transmitter on the ground. By the way, if we do this bistatic mode, we can have another 20 to 50 dB improvement in the signal to noise ratio. That means longer range or smaller object at the same range. The high resolution imaging mode for close operation, that's already been demonstrated, at least for the ground applications. So the potential applications are space debris detection, space situation awareness, and RPO, and etc. With that, that's that. Thank you very much.